So just like nutrients, water cycles through the environment, and it also has places where it is stored. And in fact, human settlements are reliant upon our ability to be able to have water year around. So when we look at historically settlements that have disappeared, maybe what appears to be overnight, it could be, for example, that they were not able to, for whatever reason, obtain enough water. So a good example of this might have been the Mayan civilization on the Yucatan Peninsula. So when we look at historical data, we see that perhaps the climate changed just enough that there was not enough precipitation, there was not enough rainfall. So they weren't able to store enough water to grow their crops. And so we see that there are just remnants of this civilization today. When we look at water, water is composed of hydrogen and oxygen. So we have H2O, and these water molecules are really interesting in that we have an oxygen, which is covalently bonded to a hydrogen. But interestingly, the distribution of charge is unequal. So this is an example of what we call a polar molecule. And one of the interesting things about polar molecules is that they form hydrogen bonds with other molecules. So for example, water molecules hydrogen bond to one another. So this hydrogen bonding could be shown here in a dotted line. So this is an example of a hydrogen bond. And it is weak. And so when we look at liquid water, for example, we see that the reason why it is liquid is that there is hydrogen bonding between the water molecules. So as you heat up the water molecules, we break these bonds and the water changes its physical form. So it goes from being a liquid and into a gas. The strong bonds between the oxygen and the hydrogens are not broken. If they were broken, if we split a water molecule, that would release a lot more energy than if we're just breaking these weak hydrogen bonds. So when we look at water, we can talk about where water is stored. And so we have places like the ocean where the vast majority of water is stored. And this is salt water, obviously. And salt water has a high solute concentration. So there are lots of things dissolved in water, but in the ocean, it is sodium and chloride and other types of salts and minerals in solution. Now, we cannot drink this salt water because what we would have to, the amount of water that it would take our kidneys to process the salt water would be it would take more water than we could even get from drinking the salt water. So you know that, for example, you don't drink salt water. It can make you very, very sick. So when we look at the other storages, so I could write these storages down. We could talk about the storage in the atmosphere as clouds. We can talk about surface fresh water. And then we could talk about what is called groundwater. So sometimes we tap into these groundwater by drilling a well. And this groundwater water actually can stay for long periods of time under the ground, but eventually it generally will come to the surface. When we also look at where this is in terms of fresh water, sometimes this is in the form of ice, for example. So we now know that, or you might know, have heard of, that the glaciers and the ice caps in the Arctic and the Antarctic are melting. And so this is actually adding fresh water into our oceans, which is diluting the solutes, but it is also going to cause an increase in ocean levels. And so we're going to see some areas of land that were not underwater that are going to be underwater. So let's look at a diagram that shows this. So here we have groundwater, and this is just the amount. So this is a value, and it is in, I believe, maybe, what is it in? What units is it in? It is in, I'm not sure the units, so we'll just go with this. So I know that that in some of the units in your book, it's like kilometers cubed, and so it's like miles cubed of the volume of the different places where water is stored. Okay, so let's look at how water moves between these different storages. So we can talk about evaporation, and we know that evaporation is fueled by the sun. So let me change we could talk about the flows. So we have evaporation. So this is sunlight, for example, beating down on the ocean, and it is going to heat up the water, and it is going to cause some of that water to evaporate up. So this is what you see, for example, right here. We see evaporation, and this is a non-spontaneous process. It's a non-spontaneous flow. So it takes light and sun and heat, right? The sun is what causes that evaporation to occur. So we have evaporation as being a flow. We can also talk about transpiration. So about 90% of our water, of our clouds, comes from ocean water that is evaporated. About 10% of it comes from what is called transpiration. So when we look at transpiration, this is the process by which plants move the water up into their roots and then out through their leaves. So the roots take in the water, and the water molecules are adhesive. They kind of adhere to each other because of those hydrogen bonds. And so the evaporation from the leaves is what actually causes the pulling up of the water from the roots. So there's like this continuous water column in the trees. And if you've ever been in a tropical place, you might notice that clouds seem to form spontaneously in the afternoons. And so water in the rainforest, oftentimes it just rains down as precipitation. The plants take it back up, it evaporates back into clouds. And so it's actually the rainforest itself that is creating the clouds above that area. And then the clouds get heavy and they release their rainfall again. So that is an example of a flow. We also have precipitation. So this is rainfall or snow. So we have rain or snow. And you probably know that it is very important in terms of specifically our water in Eastern Oregon. You probably are familiar with the fact that the ice melt, the snowpack, is really important for keeping water levels in our rivers and our streams. So what generally happens when the clouds move over from the ocean, from the Pacific Ocean, they get to the Cascades, and then they need to rise to get above the Cascades. So in order to do that, the water has to come out of the clouds. And so we see on the west side of the state, a very wet climate. And then on the other side of the mountains, there is sometimes what is referred to as a rain shadow. So say, for example, this cloud is moving inward. It hits the ocean, or it hits the mountains, and then it snows, right? And then on this other side of the mountain is where we have the rain shadows. And so this is just the way that the circulation of the air works. And the circulation of the air is also powered by sunlight and heat from the sun. So if we look at, let's see, an image here. Oops, that's not the image I wanted. Image. Here. This is another image that shows the movement of water. So as water hits the soil, it can be stored in the soil. So we could have soil moisture as being a storage. So this is another storage. So as the water moves down through the soil from rain, we have what is called infiltration. So it just percolates down through those spaces, and then the soil stays moist for a given period of time. And we're going to talk about the different types of soil and how that determines how long the soil tends to stay moist. So sandy soils, desert soils, tend to not hold water very well. Clay soils tend to hold water very well, maybe too well, right? So as the water moves down, it can then get to a point where it can't percolate anymore. So it reaches the bedrock at the bottom. And so we have what is referred to as the water table. So the water table, like for example, if you lived right next to the river, the water table might be really high. And if the river rises, for example, you might actually see puddles or pools or little wetlands forming because the water table has risen when the river rises. So there's water that's running underneath your river as well as in your river. And then when we get down to a certain point, we get what is referred to as the aquifer. And so the aquifer contains groundwater. And this is really important because this is a major water storage. And so we can tap in to aquifers. Now, the problem is that we need to realize that we oftentimes take out water faster than it gets back into the aquifer. So there are some places where we are actually mining this ancient water by taking it out of the ground. So if we look at an example of this, we can talk about the Ogala, which is the biggest aquifer we have on our continent. And it would look something like this. So notice this is Wyoming, Colorado, Oklahoma, Texas. And so this is a major aquifer, and it contains water from our last ice age. So some of the water has been down there for like 12,000 years and it's stored there. So what we do is that we go in and we mine that, we take that water out, we drill wells, for example, and we pump it out of there. And generally what happens is over time, the levels of groundwater in your aquifer decrease. So there's just no way for it to recharge fast enough for us, how fast we're taking it out. And so it's really important to realize that sustainable use of water is generally not relying upon this very old source of water.